Welcome to the Explainer. So, you know the device you're watching this on right now. It almost certainly crossed an ocean on a huge cargo ship. But before a single piece of massive steel for that ship is ever cut, it has to exist entirely in someone's mind. And today, well, it has to exist entirely as digital data. Today, we're exploring the absolutely monumental shift in how modern ships are designed and built. We're going to look at the digital tools that make constructing these 300-meter ocean behemoths possible, safe, and most importantly, efficient. Okay, let's dive right into this. Just picture a 1960s drafting room for a second. For most of history, ship design meant creating thousands of paper drawings. I mean, literally tons of paper. It required enormous drafting halls filled with absolute armies of draftsmen, all bent over their tables. It took months of painstaking manual labor just to get the blueprints ready. Now, fast forward to today's shipyard. You have one single engineer manipulating a highly complex 3D software model, producing in just 1 week what used to take an entire team several months to pull off. It is the exact same job, but we are looking at a completely different world.
Section 1. Decoding CAD and CAM, the digital translation.
Let's start with the digital brain of the whole operation, CAD, which stands for Computer-Aided Design. This is how the ship is drawn and engineered entirely in the digital realm. But here's the thing, it is not just a digital drawing. It's a comprehensive 3D database and wire model. Every single plate, every pipe, every ventilation duct, and every structural member is modeled precisely in this environment before a single torch is ever lit in the shipyard. The ship actually exists perfectly as data first. And that brings us to the physical muscle of the operation, CAM, or Computer-Aided Manufacturing. So if CAD is the digital brain, well, CAM is the brawn. CAM is the system that takes all those perfect digital designs and sends them directly to the machines on the shop floor. Those machines then automatically cut, bend, and shape the heavy physical steel. The true unprecedented power of CAD and CAM is that design and manufacturing are now directly and seamlessly linked together. Section 2. The digital to physical workflow. Journey of a part. So, how exactly does a digital concept actually become a physical reality on the hull of a massive cargo ship? Well, here is how the journey works. Step 1, the naval architect models the ship in 3D. Step 2, the software automatically generates the individual 2D geometry for every single plate, frame, and bracket. Step 3, those geometries are instantly converted into what's called a numerical control or NC cutting program. And finally, step 4, the CNC machine on the shop floor receives those exact coordinates and cuts the part. Now notice what is entirely missing from this workflow. There is zero human interpretation required between the computer and the cutting torch. And this brilliantly illustrates an incredibly powerful shipyard mantra. Draw it once, build it directly. Because the machine doesn't have to try and interpret a smudged paper drawing, but instead simply follows a sequence of XY coordinates. The translation is perfect. This entirely eliminates the transcription errors, the misread blueprints, and the incredibly expensive rework that used to just plague shipyards. It's drawn once, and the machine executes it directly. Section 3. Nesting. The ultimate puzzle, minimizing steel waste. Now, think of nesting like a giant, high-stakes industrial jigsaw puzzle. Instead of a team of workers spending days agonizing over how to fit all these weirdly shaped pieces together, and probably losing their minds of it in the process, nesting algorithms automatically arrange hundreds of uniquely shaped parts onto standard flat steel plates. They fit them together exactly like puzzle pieces. What's amazing is the computer's algorithms complete this massive puzzle in mere seconds. Just look at this efficiency. By letting the algorithms solve this massive puzzle, modern shipyards achieve an astonishing 94% utilized steel from a raw plate, leaving a minimal 6% in off-cut waste. When you consider the sheer scale and volume of metal required to construct these vessels, seeing a 94% efficiency readout isn't just some abstract number on a screen. It's a massive triumph of modern manufacturing. So the crucial point here is understanding the absolute scale of this impact. Think about this. Even just a 5% improvement in nesting efficiency across an entire ship can save hundreds of tons of steel. That is literally hundreds of tons of material that doesn't need to be mined out of the earth, refined at a steel mill, purchased by the yard, or transported across the globe. And the computer does it all automatically, giving far superior results than manual drafting ever could. Section 4. Precision at scale, the impact. So let's zoom out for a second.
What does all this precision at scale actually achieve for the shipyard? Well, because of the direct link between digital design and manufacturing, parts are drawn just once. They're nested automatically in seconds to maximize material. They are cut by numerical control machines entirely without human transcription errors. And all of this cascades into vastly faster overall production times, much higher quality builds, and significantly less material waste. Understanding this digital to physical translation is absolutely vital for grasping how modern industrial engineering actually functions today.
Which leaves us with a really fascinating, provocative thought to ponder. If every single physical part of a ship, every plate, every frame, every pipe, is born from precise digital data, what happens when we combine all of that data into a single, comprehensive master model? What happens when a ship is built entirely in data, long before it ever touches the water? Well, that takes us into the incredible world of the ship product model. But hey, that's a topic for our next explainer. Thanks so much for joining me today. Keep learning, and I'll catch you next time.